how many of you, I'm going to, this is, Stephen, I understand why you stood over here. It's a little blinding. How many of you plan on doing any work in economic theory? And don't be embarrassed not to put up your hand. Right, okay, that's kind of what I mean, how many, most of you plan on being applied economists, is that correct? Who plans on doing economic theory? 1, 2, wow, 3, 4, 5, that's like a record, okay. So I want to say something to the rest of the people in the audience just for a moment about what is the role of economic theory in economic analysis of substantive problems such as those that we're undertaking here. And I think the thing that I want to say is really very simple, is that at the end of the day, you're going to choose some empirical methodologies, you're going to carry out some statistical analyses, you're going to come up with some estimators, you're going to interpret these estimators, and then you're going to tell us at the end of the day that we should care about these estimators, okay? And most of the time, when we say that we should care about these estimators, we should care about what we found in these studies, we are really saying we're interested in more than just describing statistically the data set we've just worked on. In fact, that these estimators and what we have found, in fact, have some implications for the world outside, right, of this data set, right? And you should all know, and this is really important, that the minute you do that, you're actually making a whole bunch of theoretical claims, okay? When we move from the analysis of one data set to statements that say that there's generality here, that the same phenomena, whatever it is operative in all of these other situations, right? You're actually saying that you have some kind of theory of the world that says that these things have meaning beyond the data sets in which they've been generated. And so this is why, for example, that that if you make a causal claim, Jim Heckman famously says in a paper that's in the QJE that causality is a property of a model. Right? It's not a property in the world; it's a property of a model. And when I read that, I have to say, for me, it was a slap in the face. This is something that I'd always believed, but I never really believed it. I never said it to myself in exactly that way. And this, of course, is one of his many arts as an economist, is that he can say things like this in a way that really make you sit up. And this is true, and that causality is a property of a model. So that when we say that we believe our analysis, that our coefficients, for example, our findings are causal, right? We're actually saying something about a model. Whether or not you have articulated that model, whether or not you have written that model down, okay, you are making claims, you are making a theoretical claim. And so it's hard for the rest of us reading your papers to evaluate these theoretical claims unless we actually know what the model is. And sometimes this gets down into the very nitty-gritty of econometric analysis. And so let me give you one example of this. You all know that when we were using an instrument in a regression, right? An instrument in a linear model has to have two properties, right? It has to be correlated with the variable that you are instrumenting for, and it also has to be independent of the error term, right? Or uncorrelated with the error term. Often it is the case when we are studying some phenomena that the phenomena that we're studying is really multi-causal. We don't think that our explanation is the explanation, but it's one of many explanations, okay? Or maybe one, not of many, if there were many it wouldn't be very useful, but one of several explanations that might be driving the phenomena in question, okay? Now, if that's true, then you actually have to think about, let's imagine, for example, that we have an instrument that is not, in fact, a variable in one of the driving equations of your model, the model that you're estimating. So that's fine, that's good. So it looks like an instrument. But suppose it plays a role in some other alternative causal theory which has some degree of plausibility, which really could be going on, right? Where would you see that in the statistical model that you're looking at? How would it appear in the statistics? So we have cause A described by model A. We have cause B described by model B. Our instrument is not a part of model A, okay? But somehow it's implicated in model B, right? how does model B, how is model B reflected in model A? No answers here, right? It's reflected in the error term, right? It's some of the other stuff that is going on that we're not measuring and we're not observing, right? And so this actually creates problems for the validity of your instrument, right? If you want to argue that your instrument is really independent of the error term. So this is a simple example of why theoretical claims, having in mind a theoretical model, the theoretical model that you're thinking about when you're doing empirical analysis is very useful. This does not mean that you have to have a theory section to every paper. It does not mean you have to have a bunch of equations, right? But it does mean that these are things that you need to be prepared to talk about. It structures your thinking. I find when I talk to my empirical colleagues that the papers that they find most compelling are papers where the answers to these kinds of questions are in fact fairly straightforward. So it's my belief, and the empirical economist sitting in the back of the room can tell me whether this is true or not. But it's my belief that many of the very best papers, very best empirical papers, are theoretically well-founded, even if having a big theory discussion is not a big part of the paper, right? And so certainly it is the case that papers that are not well-founded this way are susceptible to being torn apart in your job market seminar, right? This is to be avoided. So that's why theory is important for those of you who don't plan on doing theory for life. Let's move on and talk about what we're going to talk about today. So Stephen gave a wonderful discussion this morning, a wonderful introduction to the topic of social interactions, and which in some sense doesn't leave me with as much to do as I had thought. There are competing claims about the role of sociological analysis versus economic analysis in understanding social phenomena. And I used to say just market phenomena, but then when you think about, for example, the work of Gary Becker, you realize that economists have moved far away from markets, or maybe it's fair to say have reinterpreted many things as markets. Okay. You've now had a chance to read these two quotes. Karl Polanyi was, I guess you could call him a sociologist, and you can see that his view of economic relationships is that they basically serve social ends. He argues that, in fact, the rise of capitalism changed the entire worldview, right? And that before the development of social markets, before the development of big trading markets and all of this, that people were interested in very different kinds of things, and that the creation of a capitalist economy also changed human values in a fundamental way, right? And so he says that modern man, Homo economicus is sometimes referred to, is in fact a very modern invention. Jim Duesenberry here is complaining about the way, slightly complaining, I have to say, about the way that sociology versus economics work. Economics is all about how people make choices. Sociology is all about why they don't have any choices to make. And it is true that we see ourselves, right, more generally, right, as not just studying markets per se, but we study lots of social institutions, right? We study political institutions, we study families, things like this, and we are, and the rational choice model, which has informed economics since the late 1800s, has in fact infected, and infected is actually the right word, many of our fellow social science disciplines. But this, I think, is what we bring to the table. This is why we are successful to the degree that we are successful as an analytical science. But I think that and this is a case that Stephen made this morning at greater length than I will, there is a lot of advantage to reading the other side. Okay, and Stephen was entirely right when he said this morning that to be a good economist, you need to be reading anthropology and sociology and above all history. And by the way, I might point out that when I was in graduate school, there were several good graduate programs in North America for which history was a required class, right? I believe it is still required at 2 graduate programs that are regarded as top 10 or maybe even top 5 programs. Reading outside the discipline, I think, is very important. What do we mean by social interactions? Stephen, again, talked about this at length. I'm going to be a little bit more specific than he is. I think that that we can classify most of what economists do under the rubric of social actions as falling under one of 4 categories. Social learning, how do we learn from others? Social norms, how does the society that we live in and the rules of that society, how does that condition our own behavior? Perhaps a special case, but maybe distinct, maybe not, are peer effects. I guess I think of peer effects as being distinct because there are some social norms that we adhere to where the enforcement is not the social enforcement is not necessarily by peers, right? There are rules that we have just been, brought up with that we are acculturated to, and therefore this is what we do. And perhaps if we didn't obey some of these rules, our peers would think it's kind of strange, but that's kind of not really why we do them. We do them because it just wouldn't occur to us to think about doing things in different ways. More generally, there's a class of things which we can call strategic complementarities that come from non-economic activities. And again, Stephen talked about this at length this morning. I've highlighted the last 2 by putting them in a red, a color that is actually known as Cornell red, at Cornell. And these are the 2 things that I'm going to talk about most today. This class is the title of this class is the Economics of Networks, or Economics and Networks, something like this. I am going to focus on I'm going to talk a lot about network phenomena and social networks, and which is maybe a generalization, a more general kind of interaction than just group membership. Group membership is an example of a network, but there are other kinds as well. However, the first analytical thing we're going to do is talk about group effects. So, but before we get there, let me say something about where social interactions actually appear. And I see that I am to talk to 3:25, okay, which is an hour from now. Someone is going to have to stop me. Valerie, you know this. Throw the brick. So, where do social interactions appear? There's been a number of papers in a variety of different areas where people are looking for peer effects or social conditioning of some kind. And I've listed some of the phenomena where I've recently read papers. There's a lot of a large literature in labor markets and social interactions, in particular job search, and we're going to be talking about some of these later. How do you find a job, right? So all of you you either have a PhD or you soon will have a PhD, right? And then you're going to go out and look for a job, and you're not going to really respond to an advertisement in the newspaper, right? You're going to use the social network of your advisor or the professional network of your advisor and other people in your PhD program in order to find you a job, right? This is a very networked market, right? It turns out that many, many other markets are like that, and I'll present some data on that in a little while. Fertility choice, obviously. Health, how do you get health? How do you assess your health, right? There is a famous paper that we might talk about a bit in a little while. I'm not saying it's a good paper, it's just a famous paper that asserts that obesity is contagious in social networks. Educational outcomes, there is a large literature on peer effects in education. Finally, I shouldn't say finally because this is not the last topic, but the last one on my list, is that in the study of violence in particular, for example, gun violence in America, crime waves, things like this, right? There is evidence that these things are to some degree a peer phenomena, network phenomena. What are the mechanisms at work? I put a list up here. Some of these are things that Stephen has already talked about. peer effects being one, role models. Stephen talked about role models this morning. See, I don't have to do anything, Stephen. I'm done. Call it now. Social norms, social learning. Social capital is an interesting. I put a question mark here because people have long arguments about what social capital actually is. My favorite definition comes from a sociologist named Nan Lin, who teaches at the University of North Carolina, and he says that social capital, what we mean by social capital is social capital is the resources that are embedded in our social relationships. So if we think about a social network, we are nodes in a social network, and there are edges connecting those that we are connected to. We, of course, all have our own resources, and we might call these node resources. There are other resources that are embedded in our relationship, right? That we can do things better because we are related, okay? And that's what he means by social capital. And that seems like a pretty useful analytical concept as opposed to a talking concept, right? Which fills literature. So let me give you some examples of some of these different things. And examples of what? Let's go back. Social learning and social norms. I'm going to combine those into one example. Peer effects and strategic complementarities are the other two, the two that we're going to be talking about today. So let me quickly give you an idea of how economists, in particular theoretical economists, in particular me, who's written a paper on this, might talk about social learning and social norms. The interesting question to ask is, where do social norms come from and how are they maintained? People who write on this often think in terms of describing a social norm as a Nash equilibrium, a particular Nash equilibrium of a game that has multiple equilibria, right? So if we have a game with multiple equilibria, why is it that some kinds of behavior, some kinds of equilibrium behavior are favored over other kinds of equilibrium behavior? Why is it that we are in equilibrium number 1 and not in equilibrium number 2? And sometimes an appropriate answer to invoke is a social norm. So one might ask, where would social norms come from? So here we have a simple game. This is essentially a two-person stag hunt, for those of you who might remember seeing that in a class. There's an action that you can take that just guarantees you an outcome of 1, no matter what anybody does. You know, the story of the stag hunt is that two individuals go out to hunt a deer, and it takes two people, a deer, stag. What's the Russian word? Anyone know? You know, this is an animal with horns, right? Okay, German word is reh, right? No, okay. Anyways, I'm moving on. Pardon? Okay, so these are big animals, so it takes two people to capture them, two people to hunt them down. And if you hunt one down, then you have a lot of meat, right? And that's great, and you get a lot of stuff. You get 1 plus A, right? Where A is a big number. But on the other hand, there's always the chance while the two of you are out, kind of stalking around on this different sides of the deer, your partner might see a rabbit over there, right? And he might go chasing after this rabbit. Why might he go chasing after the rabbit? Because he's going to get the rabbit for sure, because rabbits are slow and stupid. And so he'll be able to catch it. And he is not sure that he can trust you to do what you're supposed to do in the hunt. Okay? Maybe you're off rabbit hunting as well. Okay? Consequently, it might make sense for him to defect from your cooperative agreement and go chase the rabbit. And he might do the same, and that is the DD equilibrium. You'll see that DD is an equilibrium in this game, right? By the way, the way to read this table is that this is a symmetric game, and these are the payoffs to the role player, right? So if I were to completely fill in the table, we would have a 1-1 on the top diagonal element. On the lower right, it would be 1 plus A, 1 plus A, and then we would have 1-1 going down and 0-0 going across for player 2's payoffs. Right? Okay. So you can fill this in. So how are we going to actually achieve how might we come to realize a particular social norm? So the other equilibrium, of course, is that we both cooperate. We both kind of trust our partner, right, to do his job. And then if that happens, we achieve this, this greater payoff. Okay, and that's the CC equilibrium, which in the language of game theory is Pareto dominant. It's the Pareto dominant Nash equilibrium. Everybody with me? Okay, so I now want to change. I want to imagine a scenario in which learning can take place. We might imagine that there's a large population of players. So we're now kind of leaving the village stag hunt story. There's a large population of players, and they're randomly matched. They're randomly paired up to play this game. Okay, they play this game. They have some beliefs about what their partner is going to do in this particular round of the game, and furthermore, they learn from experience. Okay, now one can actually build a very complicated Bayesian learning model and never be able to analyze it, or maybe you could analyze it. But I'm going to do something simpler. I'm going to assume that everybody just thinks that they're living in an IID world, right? So I know that some fraction of the population are going to be cooperators. Some people are always, there's other people out there who are always going to chase the rabbit. And I don't know, I know that I have a random draw from the population, and some are rabbit chasers and some are not, and I have to figure out what to do. And I'm going to learn, right? So I'm going to start with some initial beliefs, a priori beliefs. And then as I experience, I'm going to revise my beliefs, but I'm going to assume that I'm drawing from an IID distribution, that every period I'm drawing from the same distribution and the draws are independent. Now, of course, this in fact is false because everybody else is doing the same thing. Everybody else is learning, okay? It may well, so I'm going to adopt this as a behavioral hypothesis about how people learn. Okay. There are other kinds of learning models. We could actually do a full Bayesian analysis. There are other kinds of learning that we could talk about. There's a model that I like a lot called the group learning, which we could bring to bear on this. And maybe we'll talk about, we probably won't, but small chance we'll talk about some of that later. I'm going to, in fact, give them a particular prior distribution called the beta distribution because it just happens to be, I forgot, what's the term? It's the, if you draw from a binomial distribution and your prior is beta, then your posterior will be beta as well, and only the parameter changes. And I forgot the term for that kind of thing. But in any event, so we're always going to have beta distributions that are going to be updated as we play. And the play the population, what we can show in this model, and I'm not going to do any of this here, is number one, we can show, did I do this anyhow? I did not. Okay. So we can show that the population will settle into one of the two equilibria. Ultimately, everybody with high probability, well actually, what will happen in the end is that the probability of playing one of the two equilibria converges to 1. Both equilibria have a positive probability of being realized as the limit equilibrium, right? And one can also demonstrate that the probability that you land in the high equilibrium is greater the larger is the parameter A, right? So the more the Pareto gains from getting into the Pareto better equilibrium, the more likely it is that you're going to achieve it. And this is, by the way, this is not a Markov process. This is not going to keep bouncing around forever. It really is convergence with probability 1 to everybody playing D, or convergence with probability 1 to everybody playing C, right? And the probabilities of converging to the C equilibrium versus the D equilibrium depend upon the parameters. They also depend upon the priors, okay? And the reason is, if you think about it, when you do this kind of updating, the more evidence you have, the less you're swayed by the next piece of evidence, right? And so once you've experienced some initial draws, it's going to be harder to get you to move, okay? So that's why you're kind of collapsing down. There's always the chance that you'll get a run of bad luck, or a run of good luck that might make you change your mind, right? But that becomes an increasingly rare possibility as the model, as time evolves. And so here we have a story, a learning story. Number one, it's social learning. We're learning from our peers. And it's also a story of how a social norm might emerge, okay? Namely, the social norm being interpreted as the idea that we're going to play the C equilibrium rather than the D equilibrium or vice versa. And if we ran this experiment with lots of different populations, we would see some populations settling into the d-equilibria and other populations settling into the d-equilibria. A lot of the ideas in this kind of literature, of which this is a representative piece, a lot of these ideas actually come from evolutionary game theory rather than from what Ken Binmore has so conveniently labeled as inductive game theory, thinking things through. Okay. All right. One more thing I should say about social learning. There's another kind of social learning model that is relevant to talk about here, which many of you have probably seen. This would be an example of this would be the Abhijit Banerjee's job market paper, for instance, where the idea is that you have to decide whether or not to go to the new restaurant in town. And so you see that there's all these people in a line. You're all living on some kind of line, and you see what the people in line before you did. They come out and they give you some information. It was either good or it was bad, right? In this condition, it's your choice. And maybe you're seeing the entire line, but perhaps more appropriately, you're only seeing some piece of the line. Right? And then the question is, what do the dynamics of that look like? And those are important models for thinking about things like the diffusion of new technologies and things like that. And we'll be talking a little bit about that later on. All right, peer effects. So I want to describe, Stephen spent some time talking in broad terms this morning about peer effects and strategic complementarities. I, anticipating this because we had rational expectations, okay, or we were in a Bayesian equilibrium, depending on how you want to think about it, decided to write down a more of a concrete model so that you could see what that looks like. So I'm going to, so here's here are two such models. Here's a canonical peer effect model. Everybody has a payoff function. This is going to be a game. It's going to be a game with n players, where n is going to be a finite number. And every player has a payoff function here, which consists of two parts. Your payoff depends upon what you do and what everybody else does. I'm not going to use this pointer. I hate it because pointers go like this. You look like you have Parkinson's disease. So I don't want to do that. The payoff function has two parts. The first two terms we can think of as a private utility, right? You get, you're going to choose the strategy space is the entire real line, okay? And you get a private payoff, which is some number h of n times s of n minus 1/2 of s of n squared. If that were the only term in the utility function, you wouldn't care about what anybody else did. There'd be no strategic interaction of any kind, and you would choose h of n, right? And since I'm going to describe, the right way to do this is with an incomplete information game, and I'm very partial to incomplete information, to Bayesian games, but I didn't, I thought it would just take too long to go through. So we're going to do here we're going to assume that we have complete information. So everybody knows what everybody else's h's are. So if there were no public component, if it was just this first little piece, each person would choose as his or her action would choose the number, person n would choose the number h of n, and that would be it. But there's another term as well, and the other term as well says there's a number which we can, this number s bar n. What is s bar n? It looks like some weighted sums of what everybody else is doing, and these weights are going to sum to 1. All right. So this is an average of what everybody else is doing. And the only way in which this generalizes, well, it's a rather big generalization actually of what Stephen talked about this morning, is that these HANKs need not all be the same number. They need not be 1 over n or 1 over n minus 1, right? It might be that when I'm computing the average, I care about some people but not about other people. So some people are going to be represented in my average with a 0, which says I don't care what they do, okay? And other people are going to be represented with positive numbers, and the whole sum is going to be 1. The natural question you should be asking is, what if there's someone you want to distance yourself from, right? How might we represent that? Suppose some of these numbers were negative. How would we think about that kind of model? And sociologists have thought a little bit about that. Economists, not so much. So that, I think, is an interesting thing to do. And it makes the game, by the way, much more complicated Because you'll notice that these payoff functions right now are all concave, right? But if you have some guys that are negative, right, it may not be that way anymore. And so stuff gets interesting. So in any event, what does the second term say? It says that, well, we can think of Sn minus S bar not n is how far away in quadratic distance, square distance, are you from the average of what everybody else is choosing in your reference group, okay? So I'm going to use the little pointer again. This is the average of what everybody else is doing. This is what I do. This is the square of the distance from that. And the farther away I am, the worse off I am, okay? And the stronger, the larger this parameter beta, which is going to be greater than 0, the larger that is, the bigger the effect, okay? So what I'm essentially doing is trading off two components here. I'm trading off a private part and a public part. And the private part is pulling me towards this Hn, which is what I would do if I were on my own, but the public component is pulling me towards my peers. All right? And now the question is, what does the Nash equilibrium of this thing look like? And we're going to come back and talk about that later. Okay? Not now. Actually, we're going to do one version of it in the next slide, but all right. Here's the strategic complementarities example. The idea of strategic complementarities is simply that my payoff, we have an ordering on a strategy space, on my strategy space, on your strategy space, and all that. And the point is that my utility increases as you go up in your ordering. Okay, and that's and we want to actually go farther. What you would like is that the real idea of strategic complementarities is that the utility gain to me choosing a higher strategy rather than a lower strategy for me is increasing, okay, in the strategy that you choose, okay? So if you choose higher strategies, the gain, if you choose a higher strategy, the gain for me in going from here up to here gets bigger and bigger. So this is an example, this is sometimes referred to as the single crossing property, right? Is familiar? Single crossing is actually a term that comes from information economics, but it's now been adopted by game theorists more generally to talk about strategic complementarities. So when you choose a low strategy, the gain for me is small, might even be negative. And as you choose higher strategies, that gain gets bigger and bigger and bigger and bigger and bigger. That's the idea, okay? And this is the formal instantiation of this idea of strategic complementarities that Stephen was talking about this morning. Now, something that I think is not well appreciated is that these two games here and here are strategically equivalent. Okay, so it is there is no way of using observational data to identify these two models, since they are strategically equivalent. And what do I mean by strategic equivalent? I mean that if you give me some ANs and beta n's, I can find GNs down here that will give me the same best response properties. And similarly, for the GNs down up here, you give me the betas, we'll get the same up there. Right? There's some parameter constraints on when this is true, because in the specification down below, equilibria won't exist if the GNs are too big, but whenever equilibria exists in the two games, they are strategically equivalent. All right, enough of this. So now let's push a little farther to talk about, just to see how this kind of stuff works out. So here what I've done is I've changed the game a little bit because I wanted to make the computations easier. So I'm just going to pretend now that instead of having a single or a group of n players, we have a continuum of players living on the unit interval, okay? And person in position h, and I see there's a little typo here, this n should not be here, that person living in position h on the unit interval has this number should be h, okay? Is that clear? Okay. And so person h, if left to himself, would choose h, okay? Even though the strategy space is the whole line, but we also have this pure effect. And we can go through here and actually compute the Nash equilibrium. And I have computed the Nash equilibrium here. And now there are some things I wanted to say about that, and I should remember this by looking at my notes. I have the habit of writing all these beautiful lecture notes and then never looking at them, so I never say what's in them. All right, so one thing I want to say is that in this game, what you should notice is that regardless of what the parameter beta is, right, the mean of the choice of the population doesn't change. The mean of the population, the mean play of the population is independent of this parameter beta. It's independent of the size of the social interaction effect. Okay? And the way to see this is I've written down the first order conditions here. Okay? And now suppose that I just integrated the first order conditions with respect to people. Okay? Then I would have h bar minus s bar minus beta. And actually, the minus beta, when I integrate this is s bar minus s bar, so it's 0. Right? And I get that h bar is equal to s bar. That's this. Okay? Once I know that h bar is equal to s bar, then I can plug this back here and I derive this nice cute little formula. Okay? Now what you see from this, though, and the reason for doing this is you see the strong effects of coordination due to social interaction. So the mean strategy, the average play of the population is always h of n. Right? But what happens to the variance of play as we increase the social interaction effect? Anybody? Those who didn't have the meatball at lunch? So just to be clear here, this is a mean, this is a fixed number, this is a random variable, this is the hn, different people have different hns, this is the random variable, right? So what happens to the, if we think about the h distribution as being fixed with a given distribution sigma squared, what happens to the variance of s as we increase beta? It's going to decrease, right? And it's going to decrease on the order of beta squared, right? So the variance of this is simply it's 1 over 1 plus beta squared, 1 over 1 plus beta quantity squared, right, times the variance of the h distribution. So the variance is shrinking, right? And this is the coordination effect of the social interaction, okay? Now, the fact that the mean doesn't change is actually an artifact of the payoff function. So here, I've chosen a quadratic. If we actually, to make things a little harder, suppose we choose a quartic. So instead of having something where your utility goes down like this, suppose it goes down like that, much steeper. Okay? I painfully did the calculations last night, and here they are. So the thing to notice now is that the all right, so I guess I don't want to really notice anything from the first order conditions. I want to say that I went and solved this whole game. And what we have here is the average play. Okay? So what was this example? So I suppose that we had two masses of people. Okay? So again, we're going to imagine having a continuum of people. 6% of them, I'm sorry, 60% of them have an h equal to -4. And 40% of them have an h equal to 6. To 6. And therefore, I'm sorry, that should be 0.4. Okay? So 60% have a value of -4, 40% have a value of 6. Okay? So the mean is equal to 0. Okay? And now you can see here that as we increase the interaction parameter, the mean falls from 0, where it should be if there's no interaction at all. It actually falls, okay? And the people who have the -4s, they come up and they then level off like this. Big fall off for the guys who are up here at 6, okay? And there's a little bit, some more facts that can be derived by going and staring at the first order condition. But the only reason I did this example was simply to point out that you can also have here kind of what Stephen referred to as a social multiplier effect. Okay? And the multiplier effect is simply that the behavior of the group is now pulling people away from their private stuff. It's pulling them in a particular direction. Okay? Now, many people refer to the to multiplier effects as being something where you actually see more of a movement in the same direction. Okay? I don't think that it's really interesting to study games where everybody has exactly the same incentives. Okay? Because this is not the way the world looks. And in games where people have different incentives, there's not going to be this clean thing where we're all going to do more than we did before because of the multiplier effect, right? What's going to happen is that different people are going to be pulled in different directions, and that's really the more general phenomena, and that's what we see here. All right, so moving on. I now want to go back to the original game with the quadratic, and I want to imagine now, let's tell a story about this game. Let's suppose that H is actually a measure of student ability, and we're talking about pure effects in a classroom. Okay, and I should say that this is an example of a model that Rashi Jayaraman, who Stephen mentioned this morning, that she and I developed many years ago and wrote a nice little thing on, and somehow never managed to publish. We never sent it out. I don't know why. It's still sitting there, and I couldn't find it on the computer, so I redid this a while ago. So here is the game. We're going to imagine now that we have this classroom, and we've got the usual pure effects story. We have a distribution of abilities, and people perform to their abilities. So basically, if there were no social effects, people would work. Maybe level of interest or engagement might be a better term for H than ability. But basically, people with bigger H's, if left to their own devices, are going to work harder or give more S, however we choose to interpret S. And so this is the same. That should be a 2 again. I did this very sloppily. I apologize. So now we're going to imagine that we divide these people. People are going to sort themselves into groups. All right? So this is the sorting aspect that Stephen referred to this morning. Okay? And in each group, we're going to have the same rule. For any given group, the mean strategy, or the individual strategy, is going to be H plus beta times the group mean divided by 1 plus beta. Okay? And now the question is, we're going to imagine there's a first stage to this game where people choose which group to join. Okay? Now the question is, why 2 groups? Why not 3 groups? Why not 5 groups? Okay? And for the purposes of this exercise, the answer is because it's what I chose to do. Okay? That would be an appropriate question to ask, maybe. And one probably that goes, it would take more modeling to really answer. So the way to think about this is, let's suppose that we have 2 groups. One group is going to have a higher mean than the other group. I think you can show that you can't have 2 groups with the same mean. Okay? And the reason you can't have the 2 groups with the same mean, this is a really stupid thing to say, but you can't find a measurable function, okay, that assigns people to you want a function from 0, 1 into high and low, into group A and group B, right, which is going to have the property that the means of the 2 are the same. And it's very there are problems in making that work, formal problems in making that work. But we're going to do 2 groups. So there's going to be a high mean and there's going to be a low mean. Okay. So imagine now in this 2-stage game how we're going to solve this. We're going to solve this by backward induction. We're going to say, okay, if we have 2 groups, what is the mean behavior in each group going to be? What is the behavior in any individual in the group going to be? Okay. And fine, we work that out and we have our nice formula here. And we know the mean of each group. Now imagine a given individual in the first stage. You can say, well, if I join the high group, this is the mean that I'm going to get. This is the mean of the group, and therefore I can see what I would do if I were in that group, and therefore how much utility am I going to get? And I'm going to call that number U. Oops, I'm going to call that number U of high. Okay, and if I join the low group, I know what the mean of the low group is going to be because this is equilibrium after all. And I know what the mean of the low group is going to be. I can compute my strategy, and therefore I can see what my utility is going to be should I join the low group, and that is this number U low. Okay? The first thing that emerges from this is that the derivative with respect to H of U high minus U low, that this derivative is in fact positive. In other words, what happens is that this utility gap is increasing in H. The value of being in the high group over that of being in the low group is increasing in your ability. Okay? So that means what does that mean? That means in equilibrium, for people with a high H, it's going to be more valuable. Well, so let's look at let me say it differently. Let's look at the gap between the utility of being in high, utility of being low. 0 is here. Okay. Here's 0. If you are I would draw on the wall, but I'm only a visitor here. So here's 0. If my h is very low, that gap is down here somewhere. It's negative. Mainly, in other words, it means that the utility of the low group is better than the high. This is going to come up like so, and it's going to cross 0, and then keep going. Single crossing property, cross at 0, right? That place where it crosses at 0, that value of h, this determines the guy who is at the margin indifferent between which of the two groups he joins. And then pushing forward as h gets higher, okay, these people over here want to join the high group, okay? And so what we have is an equilibrium sorting of individuals into groups, and this is what Stephen referred to as assortative. What you referred to it as assortative matching. I guess I have to call it assortative sorting. That the group membership is sorted by ability, and this is the other phenomena that comes out of these kinds of models, and we're going to see another example of this later. Okay. Any questions on this so far? Good. Okay, so I did some calculations here. Not surprisingly, if you use a uniform distribution, because the model is symmetric in every way, it just splits at the half, right? And people who have an h greater than 1/2, they join the high group. Lower than a half, low group. The mean of each group, of course, is 1/4, 3/4, and that's the whole story. I chose something that was a little bit more interesting, a density 3x squared. You can see that, and so this density, it pushes more people into the high group than into the low group. The mass of people who have high h's is greater than the mass of people with low h's in some sense. And consequently what happens is the separatrix moves up, right? The threshold is now a little higher than 1/2. And you can play all kinds of fun little games with this. It takes about 10 minutes to solve one of these things. All right. Stephen talked about all of this, so guess what? Moving on. Okay. So, so here's a plan for what I'm going to spend the rest of my time talking about. I have said almost everything I'm going to say about group membership. I wanted to touch base with some of the things that Stephen said, so that you can see how they work out in an analytical way. And then if you think about it and go back and look at Stephen's slides, and you can see kind of the richness of how you can interpret these kinds of models, I think you can really, by combining the analytical stuff and the interpretive stuff, you can see how this provides very powerful modes of explanation. I want to talk more specifically about social networks. So I'm going to begin by talking about some network science. And then I'm going to talk about a variety of other things on this list. If I'm lucky, I will get to here. I certainly won't get to here. All right. But my notes have an extensive bibliography. And the way that I see this lecture is I'm going to introduce you to a lot of concepts in a rather simple way. There's no way that I can, really kind of give you deep knowledge transmission in the amount of time that I have. What I want to do is I want to get you excited about looking up some of this stuff for yourselves, and giving you some places to start in the reading list. The reading list is not exactly conforming to the text of the slide, so I'm going to have to work on that before I turn it over to Valerie for final posting, but I will do that. Of course, you shouldn't constrain yourself to the reading list, but constrain yourself just to the part of the slides that I'm going to talk about, but you might be interested in looking at them all. I should give you one word of warning. I've used these slides for a number of talks on this topic. I have never gotten actually beyond here. Okay, so I have no idea what's in this part of the slide. Right. So any errors or anything stupid or anything interesting that you might find, let me know. Okay. All right. How do we describe social networks? Social networks are really complicated things, right? If we think about our social relations, there are different people that we react to in different ways. We can rely on them for different kinds of things. I have Some of my colleagues are my friends, some of them are not. Some of them are my friends, but I would never lend them money, you know, so on and so forth. It's interesting to see how, when we look at different kinds of communities, how people use social networks, right? So at least in America, in lower income neighborhoods, people might use a network of friends in order to provide them with emergency child care, right? In wealthy communities, that's not the case. That's the social norm. Here we are again with norms, right? So how people use social networks are very different. So networks are very complicated kinds of things, right? Networks also, we should remember that networks are not really static things. Networks appear in time, and they ebb and they flow through time. There's a very nice paper in Science by Duncan Watts and Yuri Kosinets. They had data from an anonymous university called Columbia, 6 months worth of, actually yes, an entire semester's worth of, or may even have been an academic year's worth of email data, hashed, we hope, okay? Who sent emails to whom? And what they did was they wanted to see what the network looked like. Well, how would you use data like that? So what they did was they said, let's see who contacts each other on a weekly basis. So what they did was they went through the data looking for things that recurred regularly within a window of a week. And then they drew a network for that, okay? If the fraction of weeks within which you contacted somebody was sufficiently high, you got a link in the network, right? And then they did the same thing, I think they did the same thing for days, then they did it for months, and then they did it for semester, and the semester was not so interesting because they only had 2 observations. But the point is that as the window changed, okay, the network changed dramatically, right? There are some people that we talk to every day, right? There are other people that we talk to maybe every month, right? And no more than that, right? So some of these ties are very strong, others of these ties are very weak, and it's exactly this insight which has driven a variety of interesting work on job search that we'll be talking about later. Having said all of that and hinting at all of this richness, we're just going to describe a network in a very simple way by saying it's a graph. There are things called nodes, there are things called edges. Nodes represent individuals, edges represent relationships, so there is a connection between us, if and only if there is a little black line. We can draw 2 kinds of graphs. We can draw directed or undirected graphs. And a directed graph says that A has a relationship to, in this graph over here, A has a relationship to B, but B does not have a relationship to A. All right? Over here, we're thinking about looking at symmetric relationships. Okay? If I know you, you know me, right? Okay? But I might claim to be your friend, but you might not even know who I am, right? Okay. The degree of a node, and now I'm going to give you a little boring terminology which is going to help us later on in the talking, so I will try and do this quickly. How many of you have actually read or studied up on social networks? Because if enough have, we can just move on. But unfortunately, not enough have. Okay. But a good number have, so I'll be kind of quicker than I might otherwise go. The degree of a node, as you know, is the number of edges, and I'm going to define things. I'm going to think mainly about not entirely, but mainly about undirected networks, because I don't want to get into, you know, the more complicated terminology that's necessary to talk about directed networks. But the ideas are very similar, no surprises. A path is an ordered list of nodes, so I can start at A, and I can walk down to B, and then I can walk over to D, so A to B, B to D, this is a path. A shortest path between 2 nodes is called a geodesic. So if I look over here, the shortest way to get from C to D is to go up to B, and so the distance from C to D is 2. Okay? On the other hand, but it's not the only path, because I could have gone from C to A, then I could have gone to B, then I could have gone to D for 3, right? Or I could have gone back and forth a lot, right? And then gone up here. So there are paths of arbitrary long length, but the shortest one is a length 2. Okay. All right. A subset of vertices of a graph is connected if there is an edge between every 2 of them. So here, this is a connected subset of vertices, it's connected set of vertices because there's a path from any one vertex to any other vertex. A component of a graph is a set which is connected and furthermore maximal with respect to this property of connectedness. So there's no other node that is connected to one of these guys that we've not already accounted for. Okay? So for example, if I just look at these two nodes, this is a connected set, but it's not a component because these guys should also be in the component. Okay? Clear? All right. A clique is a component for which all possible edges are in E, and this is like a group. Okay? What Stephen was talking about this morning. All right. It is useful to represent, to have an analytical representation of this, and we represent graphs by matrices. There are several different ways of doing this, each with their own uses. What I'm largely going to use today, in fact entirely going to use today, is something called an adjacency matrix, which says simply that there is an edge, there is an element, an adjacency matrix, simplest version, sometimes also called a social matrix, is a matrix containing only zeros and ones, and there is a 1 in the ij position if and only if there is an edge going from I to j. So I'm now describing a directed concept. Okay? If my graph is undirected, then if there's an edge from I to j, there's implicitly an edge from j to I, right? So the matrix will be a symmetric matrix. It will be equal to its transpose. If aij is equal to 1, then aji is equal to 1. Okay? And so that's what we have here. And I believe, yes, this to me looks like it is symmetric. So this is, here's a graph containing these two connected components. These two components. Here is the adjacency matrix for this graph. Okay? And I don't think it matters. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And so this is the matrix representation of that. A weighted adjacency matrix has non-zero numbers corresponding to edges in these, rather than necessarily ones. And these non-zero numbers might have different interpretations. So for example, in the game that we were talking about earlier, or when we were describing strategic complementarities, when we were describing pure effects, the aij is the amount of weight that person I puts on person j. Okay? So if you are not important to me, you have a small aij. If you're very important to me, you have a large aij. Okay? So that was an example of an adjacency of an adjacency matrix, a weighted adjacency matrix. Okay. I'm sorry, are we still connected? Yes. There is a great deal of interest in describing social networks. Stephen put his finger this morning on a topic that I think is crucial. That is that many of the social networks, many of the phenomena that we want to study take place in social networks that we have little or no information about. We might observe bits and pieces about them, we might sample little bits and pieces about them, but we cannot, for instance, know anything, we cannot see the entire network of people who are looking for a job in the Boston area, in Newton, Massachusetts, in the late 1960s, which was the data set that Mark Granovetter used for his famous study called The Strength of Weak Ties. But maybe you can infer some things by sampling bits and pieces of a network. And there's a large and growing literature on this, which I'm not going to talk about here, but I can give references to anybody who would like to know more about it. Actually, we will talk a little bit more about it in a moment. These are, so nonetheless, whenever we can look at a network, we like to look at them, we like to measure them if we can. And here are things that we might, in fact, different things that we might want to measure. Obviously, measuring how big a graph is, what is the maximal distance between any two people in the network, what is the average distance between any two people in the network, what do the properties of connection look like? This is a complicated thing to study, right? So one way of studying this is simply to say, well, how many people am I directly connected to? What's my degree? How many people are as connected as I am? Right? And if I start at, and how many people are more connected than me, and how many people are less connected to me than me, right? Once we start asking questions like that, we are now talking about looking at the distribution of degrees of the graph. clustering coefficient. This is a very interesting concept. There is a statement due to a well-known sociologist whose name, of course, I'm blanking on at the moment. Do you remember? Who?
Bonasich?
No, this is not Von. No, it's earlier. And I don't remember who it is, but it's not Phil. And the claim is that the friend of my friend is my friend too. And it's the person whose first name starts with A, which is really useless to know. But I'm sorry, that's the only bit that hasn't disappeared up here. All right. What does that say? That the friend of my friend is also my friend. It says that friendship is a transitive relation. It says that if I am a friend of Stephen's, and Stephen is a friend of Shlomo, then lo and behold, I must be a friend of Shlomo. I hope so. All right. So that's transitivity. So it is alleged, and there's empirical support for this, that there is a lot of transitivity in social networks. So that you see a lot of what we call transitive closures. Now, what is a transitive closure going to look like if we have a node here and a node here and another node up here, and we've got a line from here to here, and we've got a line from here to here, then there should be this line too. So we can find triangles where we've got, two sides, then in fact transitivity says the third side should be there as well. So we might ask the question, if we average over vertices, what is the number, what percentage of these triangles are actually closed? These potential triangles are actually closed, right? That is a measure of the degree of transitivity of the graph, and it's called the clustering coefficient, okay? And it matters for a lot of stuff, okay? And here's a graph that I'm not going to spend any time talking about, which demonstrates some of these things. But I don't want to take the time to talk about it. I think these concepts are kind of intuitively clear, and we're not going to work with them in any detail. You can come back and read this. Now, what I've described so far is very useful for talking about a single graph that I happen to be looking at here. There is a whole literature in sociology where someone whose name is often Stan Wasserman goes into a high school and gets the graph of friends, okay, and then does all kinds of statistics on it. And so that's a way of describing what I've talked about, is a way of describing single graphs, okay? But of course, we are economists, we want to do inference, right? We want to make assertions about what might be in the graph that we can't see from those things that we can see, right? So suppose I want to study something about social networks in villages in developing countries so that I can say something about the diffusion of new technologies. Well, I'm not going to go to every single village in the country, right? Because my grant is not that big, all right? But what I might do is try to survey extensively some social networks and then make some inferences from that about what social networks in other villages look like. Make sense? Right? So in order to do that, I need a probabilistic model of networks. Okay? So now we're going to move from graphs to what we will call random graphs. Okay? And what is a random graph? A random graph, think about what is a random variable. A random variable is a function from some measure space into the real line. Okay? If we have random vectors, right? It's a function from some measure space into a Euclidean space of some given size, okay? We can think about, if we want to talk about random graphs, we can talk about a function from some measure space into the set of adjacency matrices, right? It's obviously something that we can construct, right? So now we have a probabilistic model of graphs, and we can start making assumptions about those random variables, and then do all the kinds of statistical analysis and inference that we like to do, right? So this is a field called random graphs, and random graph theory is a burgeoning field. And for those of you who really want to know something about random graph theory, there is a very good book by a guy named Rick Durrett. And I think the title of Rick's book is Random Graph Theory. And he is a very amusing writer. He's a great teacher, by the way. I've studied with him. And Unlike physicists who write on this stuff, he actually proves the theorems. So you can really see how stuff works. And when you read this stuff, you're really glad that there's a guy like Rick Direct who's out there proving the theorems, because you don't want to do it. It's really, it's ugly even by the standards of probability theory. So, but there's a lot to be said about them. And what do we want these random graphs for? Well, I've written a bunch of reasons why. The village example is having observed the data from some networks. What can I infer about the properties of other networks, social networks in different villages? Also, having observed data from some part of a network, what can I infer about other properties of the network, right? So, suppose I want to study the population of drug users here in Moscow. How would I do that? Well, I can't go out and survey all of the drug users, but what I might do, for example, is find some set of drug users and find out about them and look at their relationships and then begin to infer. This is also a way of there's related to this, there is a technique called Snowball Sampling, where you find one drug user and then you say, who are your friends? I don't know why you would expect to get an answer to this, but you do, apparently. Sociologists do. And then you go and you talk to some of their friends, and this is a way of kind of rapidly exploring what this network looks like. So that would be an example of where this would be a useful thing to do. There are two kinds of models that one sees that one might use to talk about graphs, families of random graphs. One kind of model, essentially, I think of as being the graph theoretic analog of descriptive statistics, right? Which simply says, here are useful distributions of graphs, right? Now go estimate their parameters, with no thought as to where they might come from. And I've mentioned some names here. Some of you who've read in this literature might be familiar with things like exponential random graphs. Matt Jackson has a recent paper on them. Stochastic block models have been around for a very long time. But there are also what I think of as structural models of graphs, which are models of network formation. And these come in two kinds, and I'll give you an example of in just a moment. There are algorithmic models that simply say, here is a mechanism for constructing a random graph, okay? And you carry out the algorithm, and at the end of the day, you have an instance of a random graph. And I'll show you an example of that in just a moment. What we might want to do, because we think that everything in life is purposive, is we might want to say, well, what about strategic network formation? Okay? Can we imagine, for example, games of network formation, right? And this leads into an interesting literature that we're not going to talk about very much today, maybe just touch on. All right, there's nothing that's really interesting on this slide. Can I move on? Okay. So let me give you an example of an algorithmic construction of a graph. I'm going to describe what's known as an Erdős-Renyi random graph, also known as a binomial random graph. The idea is that I have a coin. It's a biased coin of some kind, probability p. I get a heads, probability 1 minus p. I get a tail. So what I do is I choose a pair. I'm going to do this for an undirected graph, but we'll do this for directed graphs as well. I take a pair of people. You're my pair. I flip the coin. Heads, you're linked. Okay? Boom. Tails, you're not. And that's how we construct the graph, right? Everything is IID. So the probability that any possible edge appears in the graph, okay, is P, and the appearance or non-appearance of every edge is independent of the appearance or non-appearance of all other possible edges. Okay, so these are not just well studied; they are excessively studied random graphs. But they exhibit properties. These binomial random graphs exhibit properties that that appear in more general graphs as well, and so it's useful to know something about them. So when we think about random variables like this, the first question that we often want to ask is, what is the large N behavior, right? You know, if we have like 5 people, what is there to say about, you know, a binomial random graph, right? With 5 choose 2 possible edges. But we might want to ask, well, what happens when N is very large, right? If we have a large population in a binomial random graph, what does that graph look like? What can we say about its shape, its texture, right? It turns out there is a lot. Now, one way we could perform this experiment is simply to say, okay, we're going to fix P, and we're just going to let n get very big. And that turns out not to be very interesting, because what is the number of edges that we are going to, what is the degree of any one person in this random graph going to be as n gets large? Right? NP, right? That's the expected degree of any individual. That's not so interesting, right? So in the end, we have a whole bunch of people with very, very, very many connections. So maybe a more natural thing to do is to say, let us grow the graph in such a way that the degree, we're going to add more and more and more individuals to the graph, but let's let the degree of the graph, the average degree, remain constant. Okay? So the way to do this is that if I'm a single individual, there are n-1 other people out there that I could link to, right? So the upper bound on my degree is p times n-1, or I'm sorry, the upper degree is n-1, the upper bound is n-1, the lower, of course, is 0. What I'm going to do, what is the mean? The mean is p times n-1 for every individual. What I'm going to do is I'm going to grow n and I'm going to shrink p in such a way that p times n-1 remains constant. And what does this remind you of? The statistics mavens in the room? What does this make you think of? When I think about having a binomial distribution, and now I'm going to grow n and I'm going to shrink p such that the mean of the binomial distribution remains the same. What do I get? Right, I get a Poisson distribution, right? And so this limit that I've just described, it's the same thing. Everybody's mean degree is remaining constant. These limit objects are sometimes called Poisson random graphs. It's the same thought experiment. Okay. Now, what are these graphs? What does a typical instantiation of one of these graphs look like? So what I mean by that is I reach into the urn and I draw a graph. What does that graph look like? Okay. Well, it's pretty cool, actually. The answer depends upon z. When z is less than 1, z is going to be, you've now read the slide and you know that z is the mean degree. Okay? When the mean degree is less than 1, our graph is going to contain a large number of small islands. Right? We're going to have little components, little connected components floating all around. Okay? And that's going to be, and so we're going to have these islands sitting in a stream. How big what do these components look like? Well, the size distribution of the components is going to be exponential, and people have even computed it. I don't remember what it is. Okay? So we have a large number of small islands floating around. Now let's ask what happens when z is bigger than 1. When z is bigger than 1, something cool happens. A continent emerges. Okay? So what we see is the following, and this is kind of a little bit complicated to explain. If we look at all of the components in the graph, there's going to be a largest component with respect to size. Right? The size of that largest component is going to grow linearly with n. This thing has a name. It is referred to as the giant connected component. Okay? And the giant connected component is with probability, I believe it's with probability 1 unique in the limit. For many, under very, very general assumptions. Those of you, people who study percolation actually write about this as well, and you can read about it there. There's a giant connected component that grows linearly in n the population size. Then we have all these other little, then we also still have a bunch of islands that are floating around, right? And the islands, again, have an exponential distribution, and I believe that their size, the mean size of islands grows like log n or something like that, okay? So we have a lot of islands. We have this big continent that emerges. Now this continent might cover only a very small amount of ground. If z is very, very near to 1, this continent could contain only a tiny fraction of all the n nodes that are out there, but its size is linear in n. Okay? When z is larger, of course, right, it contains more and more and more, and as z converges to 1, right, ever more of the mass is getting in there until in the limit, I suppose, everything is connected to everything else. That's our story with these random graphs. And so what I've done here on the right is I stole this from the internet, a little plot. On the bottom we have z going from 0 to 3. And on the side we have, going from 0 to 1, the fraction of nodes in the giant connected component. And this was the result of simulations done on 300 nodes. And you can see that the fraction of nodes in the large component is very small until z crosses 1, and then boom, it gets big. Okay? So this is what we mean by the, and this is an example of what Stephen referred to as a phase transition. Okay? So this is not water freezing, this is people hooking up. Okay? All right. There are other models. A model that has been popularized. So a feature of many graphs that people have studied is that when you look at the degree distribution, it seems to be a power law of some kind. So some of you have heard of Zipf's law, which has to do with city size. Wealth distributions, it is alleged, have thick tails, power law distributions. Degree distributions in graphs have thick tails. Okay? In many graphs have thick tails. And so there's a model called preferential attachment that is a way of generating it. I've described preferential attachment in this slide, but I think we are near to our break time, so because you're standing here and Valerie is getting antsy. So I am not going to bother to describe preferential attachment. You can read the slide. There are many models that actually float around under the name preferential attachment, and I think this is not the best, but it's the one that I can put my hands on easily. So it's what it's on this slide. Here are some pictures of what preferential attachments look like. The preferential attachment graphs and instances of them look like. You have these people who have many connections, and then other people who have very small. You see that you get this clustering. One place where this has been studied in detail is in citation graphs. So there is a link. It's a directed graph. A citation graph is a directed graph, and I link to Dimitri if I cite one of your articles. Okay. And if you look at these, at what we call for a directed graph, the in degree, who connects to you, okay, who cites you, okay, we see this kind of power law thing where there is this thick tail containing papers that have incredibly large numbers of citations, right? May you be in the upper tail. Okay, and then we have, of course, then there's the rest of us, down here. All right, with not so many links, right? So this is our favorite, your favorite papers, and these are the ones that are okay. So this is where this is an example of preferential attachment, and so it's a fun model to look at, and this is a good place to stop. All right, I want to talk a little bit about some of the consequences of social networks, and I want to show you an example of what Stephen referred to as a social multiplier. So this is a well-known paper that people interested in crime might want to read, and I actually want to look at my notes in just a second. I think what you'll discover when you teach a lot is sometimes there are things that you want to say in very particular ways, and so you actually write them down. And then when you do that, okay. So in the United States in the 1980s, and I don't know whether this is still true today, I suspect it is, there is enormous variation in crime rates across cities. Okay, and this is kind of a puzzle, or at least it was a puzzle back in the early 1990s. If the incidence of, if we thought about a model, a micro model of criminal behavior, and we explained every individual's propensity to commit a crime by looking at their individual characteristics and then some idiosyncratic term, when we look at we then aggregate up and look at crime rates in cities, okay, we would see that there's going to be variations in crime rates, and these variations in the world that I've just described, this IID world or conditional IID world, this variation would be described by variation in the distribution of correlates, distribution of characteristics in these cities. But in fact, the variance that we see, or that we saw at this time period in the crime rates across cities was in fact much larger than one could explain by variations in characteristics alone. And so this was really kind of a puzzle. These authors, Ed Glaser, Bruce Sacerdote, and Jose Schenkman, had an idea, and their idea was that crime is not IID. That crime is kind of a group activity, okay? When I am surrounded by people who commit crimes, I am more likely to commit crimes. Now, and what they do is, in this paper, and I'm going to describe their model in very brief detail, is they show how it is the case that having some kind of pure effect can in fact increase variance, right? And explain this empirical fact about a crime rate. Now, there is a puzzle. I mean, to say that we can explain something just means that we have a model that fits the data. It doesn't really mean that it's the right explanation. And I think one criticism of this paper is that when you look at micro studies of criminal behavior, right, those done by criminologists, if you look at juvenile crime, you see that that pure effects are very important in juvenile crime, and they're also kind of complicated. And there's very rich and interesting literature on this. The evidence that I've read suggests that there is not, in fact, strong evidence at the micro level of pure effects in adult crime. All right? So if these guys were to be right, okay, it would either be because, it would have to be because most crime is being committed by children, right? And that's not, of course, in fact the case. So the fact that this model fits the data, or this explanatory force fits the data, doesn't mean that it's necessarily the right one, okay? It's not as if they then tested several different models and thought about how to identify model A versus model B, and then, you know, did some kind of inferential exercise. But nonetheless, they made the point that this is one place to look for this increase in variation. So here's the model. Now, this is actually, remember, not a sophisticated model of crime. I think this paper shows us a very elegant way of using a model. The basic idea is, right, that pure effects, mimicry, imitation, that these can in fact increase, can cause this kind of cross-sectional increase that we see, right? It could be a source of this. And to illustrate why that would be true, they build a model which is not in the least a model of what they want us to measure, but it is a model that illustrates very clearly the phenomena that they want to talk about. Okay, and then they go on and do some basically descriptive statistics to suggest whether this kind of explanation is plausible or not in a number of different data sets. And there are several follow-on papers where they did this at great length. Okay, so what does the model look like? So here's their story. We might imagine that there are 2n plus 1 people who live on an integer lattice at these points from minus n to n. Okay, so we have 0 in the middle, minus 1, plus 1, minus 2, plus 2, so on and so forth, out to minus and plus n from your perspective. And these individuals fall into 3 types. There are good people, people who just never commit a crime, nice people, okay? Some of us might even know some of these people, okay? Then there's the hardened criminal types, okay? We're all naming names here in our minds, right? These are the people who just, you know, they're just going to do what they're going to do, okay? And then finally we have the great mass of people who are influenceable. Don't use that word. It's not an English word. There are people who can be influenced, okay? And what do I mean by that? What everybody is going to do is look to the neighbor on their right. Yes, on their right, okay? And they're going to see, what did that neighbor do, okay? If that neighbor committed a crime, then they're going to say, I can get away with it too, okay? And so they're going to imitate the neighbor on their right, their neighbor will imitate them, and so on and so forth. So we have this line, and we have these people of three different types distributed in an IID way on the line in these different positions, okay, in different positions on the line. And everybody looks to the right and imitates whatever it is that their neighbor will either acts according to their type, which is to say they're going to be good or they're going to be bad, no matter what, or they imitate the person on the right. And I suppose that in order to kick this off, the person at the far end of the line has to be one of these people who is of a hardened type. Otherwise, the guys, no one else would know what to do, right? So that's basically the model. So if we look here, we'll say that red guys are criminal guys, blue guys are white guys, and black people are influenceable, or can be influenced, all right? So how is this going to work? This fellow is a hardened criminal type. This person looks over here and says, ah, criminal. I can be a criminal too, so he commits a crime. She looks at him. He's a criminal, he committed a crime, I'm committing a crime too. And now the chain stops, we get to this guy, oh, but he's a good guy, he's not influenced by anybody. Okay, so that's the story of the model. All right? So now what we want to ask is, what did the statistics, what did the aggregate statistics of this model look like? Okay. Now the key thing to understand about this model is that the now what we are going to see, instead of individuals making decisions, we're essentially going, whether you should commit a crime or not, which would be the case in an IID world. In an IID world, you would choose independently. Now what's going to happen is that we're going to have these blocks of people, right, that are influenced, and they're going to be, and their decision is going to be made by looking at the first person on their right, okay, who is not an influenced person, but is someone who is a hardened type, good or bad, okay. So instead of having single individuals, we're going to have the way to think about this is that instead of having IID individuals, we're going to be having IID blocks of random size. Okay? Now that's a model that's easy to do some calculations in, and I've done the calculations. I haven't carried them out, but I'm telling you what the answers are. P0 is the probability of a criminal type. P1 is the probability, I think is the way I did this. Maybe I even said it on the previous slide. Type 1s always commit crimes, yes. Zeros are the good guys, 1s are the bad guys. So this is the probability of being a, what did I just say? I've just forgotten, yes. This is the probability of being a criminal conditional on being one of the committed types. Okay, so that number is P. Okay. So you're in a block, right? If you're a person who can be influenced, you are in a block. And the person who's determining what that block is, the first non-influenceable person on the right, that person is a criminal with probability P, and a good guy with probability 1 minus P. So your block is criminal with probability P and good with probability 1 minus P. So the mean, here is an expression. So now what we want to do is we want to say, what is the sum, right? What is the sum of criminal activity here? And the sum is represented, I guess what I've done here is looked at, this is the average criminal activity. And we can explore this random variable. It's the normalized variance of this. It's this thing here that we want to look at. We want to look at its random. We want to look at its variance. If we can do the computation, if all the blocks are of size 1, which is to say that everybody is either criminal or not, this is the standard, first statistics class exercise that you do, and the variance of the crime rate is P times 1 minus P, the usual binomial formula. Okay. What happens if, in fact, we have this correlation structure? You can do the calculation. It's in the paper, and it's P times 1 minus P times a factor okay, which is 2 minus the probability of being a hardened type, a committed type, divided by that. The point is that this is a number that has to be greater than 1, okay? Right, you know, pi here can be at most 1, okay? And as pi shrinks, these blocks get longer and longer in size, and therefore there is more correlation, right? And because of that, then the variance across cities increases, okay? All right, remember, this is the whole story, okay? So this is very simple statistics to work out. You can read the paper. The reference is in the bibliography at the end of my slide pack, which will be posted. And you'll see they work out several other examples of this. They say, suppose that you look both to the right and to the left, and you are influenced by the average of the right and the left, and they work that out. They do some other things, and they have a way of taking this to data that I'm not going to talk about. What they do is they estimate what they essentially, they attempt to make an estimate of this magnification effect. They say that due to social interactions of this kind, the variance should be some number lambda times the true variance, the variance that you would get in the IID case, and then they try and estimate what that lambda is. And they do it in, maybe not in that paper, but in another paper, they do it not just for crime, but they do it for some other kinds of social phenomena as well, other kinds of phenomena more generally as well, some of which, for which you would expect there to be a social interaction, and others for which you wouldn't. And they say that, gee, there's truth in this explanation, because when we apply this methodology to something where we don't expect to see these kinds of pure effects or correlation effects, indeed, lambda is very, very close to 1, which is to say that it's just looking just like the IID world. But, you know, for the criminal data sets, they look at this number, 2 minus pi over pi, is a very large number, right? Something like in the hundreds or something like that. So, in any event, this is an example of a magnification effect due to correlation. This is an example, I think, of it's basically what the social interactions are doing is magnifying the consequences of the fixed agents. Okay, you're not getting these fixed agents averaging out within a city, right? Because if only a few of them are driving the whole city, and so therefore we're getting much more variance. And this is basically, this magnification effect is what's been referred to as, is an example of what's been referred to as a social multiplier. All right. Let me talk about another application of network analysis. This comes from a paper by Tim Conley and Chris Udry that was published, I think it was in the AER in 2010. And this has to do with the spread of a new agricultural commodity in Ghana, eastern Ghana, I think. Here's the situation that Ghanaian agriculture in the processes in the area in which Tim and Chris worked largely focused on producing maize and some other crop, I don't remember what it is, for local markets. Okay, and then at some point, I actually have this written down, so I might as well get the dates right. It would be fun. I guess this was in the late 80s, but I don't seem to say. Okay, in the late 80s, I think. So they were growing maize and cassava, and for local markets in eastern Ghana. And then some people came and introduced pineapple, and the idea was to grow pineapple for consumption in Europe. Okay, there was a technology that worked in Ghana for intensive production of pineapple, but this adoption of this technology, you don't grow pineapple the same way that you grow maize and cassava. In particular, you needed to apply agricultural chemicals, in particular fertilizer. So People had to learn these new technologies. They had to learn how to handle them, so on and so forth, right? And ultimately, then they had to decide whether or not they wanted to grow pineapple or grow cassava and maize. So how do farmers learn about a new technology? They learn about it through their own experimentation. They might take a plot of land and try it out, or they might kind of try it for a year. This is pretty risky if you are a smallholder farmer, but you might. There's also, Ghana has a well-developed extension service, agricultural extension. So what I mean is that they have people who are employed by the government who know and study and demonstrate best agricultural practice. And you can go to them and get advice. I'm sure that most of you come from countries that have such a service. We have one in the United States. I know that they're present in many African countries. And in Germany, I guess I know that too. And that's about the extent of my knowledge. Okay. The other place you might learn, not surprisingly, is you might learn from what we call social learning. You might learn from what your neighbors are up to. You might watch what they're doing. Okay. How would we model this? Well, there's a bunch of papers out there, references here, I think. And here's how these models all work. A village is a learning unit. Okay. Some farmers experiment, others do not. Each farmer in the village looks at all of the other farmers in the village, okay, sees what they're doing. Farmers then update their own opinions regarding the new technology, and then makes a decision about what to do for the next season. Sound like a plausible model? Yes? No? Who would be tempted to say, no, this is stupid? We are all just kind of waiting for some. No one has an opinion, really. Okay. So this seems to me, if I were studying this problem, this would be my, once I account for things like extension and something like this, if I wanted to think about social learning, this would be my baseline model. Everybody looks, these villages are not that big, right? I would just, this would be your first operating assumption. Certainly, it would be maybe the easiest thing to take the data among all the social learning models you could dream up. Okay, and here's a bunch of papers that did exactly that. Every one of these every one of these authors is extremely distinguished. They know what they're doing. They're not idiots, and this is the model that they chose to estimate. And so this is a model, in fact, that Tim and Chris took to the data. Aha! Mid-1990s, not late 1980s, okay? And so what they did was they got a bunch of data on farmer decision-making inputs and outputs. Then they also got a bunch of data, and they actually collected this data. I mean, they walked around and talked to farmers. Well, they didn't, but graduate students did. They did a little bit. They collected all kinds of information on what farmers were learning about stuff and who they were talking to. Okay. The researchers performed the following experiment with the data. So they have data on a whole village. Okay. So what they did was they took someone who filled out the survey. And then what they did was they chose 10 other people in the data set at random. And then they asked the question, which you could answer in the data set. If I had chosen you, okay, and I had chosen 10 other people out there, I could look at the data and say, did you talk to him, her, so on and so forth, okay? And if the whole village was interacting with each other, you would expect these frequencies to be rather high. Right? And in practice, you can see only 11% of these matches had any of the two individuals ever talked to each other about farming. Okay. In only 30% of the matches did one farmer even say that he could think of doing that. Right? Not whether or not he did it, but whether it would be something that would even be plausible for him to do. You could be the kind of person that I don't talk farming with. Okay? That we're not close enough to share information about fertilizer. And then what about the quality of the data that you got from your random people? The quality was not very high. Okay. So this is not and yet on the other hand, there were some connections that were very, very fruitful. There were people that farmers said they did talk to at length. Okay. So what do we learn from this? We learn that information flows not at this big village sharing level, but through a very sparse social network. By a sparse social network, I mean a network with a bunch of edges. The number of edges is small relative to the number of possible edges one could have. Right? That social matrix has mostly zeros, not too many ones. All right? So here is actually a picture. Now this is a rather ugly picture of a network. I'm going to show you some pretty pictures of networks later. But there's a reason why this is ugly. This is ugly because these people are basically, this is a particular village or a sample from one of their data sets. And these dots, the location of these nodes, actually represent where the villagers live with respect to each other. And here's the scale of a kilometer. And you can see that there's a lot of kind of local stuff here going on. You talk to people near you. Here's something that's kind of surprising. These guys are all very near to each other. They don't talk to each other. Okay? And then there are some people, this looks far. Must be a relative, right? And that looks really far, right? So this is what the network of whom talks to who talks to whom actually looks like. Okay. So then what they did was to build a model, or to think about building a model where, and I'm describing the model here very quickly. There's random shocks in production. Inputs are put in today, outputs come out tomorrow. No surprise, farmers are Bayesian. This leads to a model that you can take to data. And here basically is a description of the findings. I don't really want to spend any time talking about them, but the point is that what they are able to uncover, okay, is that there is a great deal of micro detail, okay, to who talks with whom. Furthermore, the shape of the network of who talks to whom has a big impact on the nature of information transmission. Okay? Different kinds of information go through different people. Okay? But moreover, if you took the baseline Bayesian model, which I described at the outset, okay, it turns out to perform very badly against the data. Right? Whereas a model that takes network structure into account looks much better. What do we learn from that? We learn that network structure actually matters a great deal. And therefore, we learn from this something that I think that development economists and agronomists and other people have known for a long time, and that is that if you want to introduce a new technology, right, get the word out about something, you've got to approach the right people first. Okay, and get them on board. And once you get them on board, okay, you can then, you might have more luck spreading your data. So there are policy implications to be had, right, from this kind of study. Namely, what is the most efficient way? What is the least cost way of getting information out there? Okay. Let's move on and talk a little bit about some properties of social networks. This is actually a chart that I don't want to talk about. So here, let's start here. So this is a picture of a social network. This is a dating network in an American high school. Okay? Pinks are female, blues are male. Okay? Peter Behrman, who's a sociologist at Columbia, was one of the authors. I don't remember who. Yes, Jim Moody, and there's another guy, Snowball, whom I don't know. They're the authors. This paper was written in 2004. And so you'll notice that, just to be a little bit clear about this, so here we have 63 couples that were stable throughout the period of the survey was being constructed. On the other hand, we have some people who are real social butterflies. Right? they're having a good time. Right?
And this admitted that 95% didn't go on dates.
95%?
It omitted the 95% of the students who had...
Who actually had, right, who were like us.
Yes.
Yes. you know, there was a surprising, it turns out, this seems to be something that sociologists claim is one of these, it's a stylized fact. We all know what stylized facts are in economics, right? Apparently, a stylized fact in the sociology of high school dating networks is that no one dates when X is X. Figure that one out, right? Draw the picture. And you don't see any of those links here. I did not. I am not sufficiently compulsive that I would take the time to check that. But the thing to notice here, again, is that we have what we might call a giant connected component, right? This is very close to something that what graph theorists call a spanning tree, okay? A minimum size graph that covers a given set of nodes is typically going to be a tree, okay? And if you cut this in not too many places, you have a tree that connects all of these. And again, we have a giant component here, and then we've got all these little islands here, 12 of these, 63 of these, so on and so forth. Okay? So this, even though it is certainly the case that no male-female couple is flipping a coin to decide whether or not they are going to partner up during this window, this graph shares many of the properties, many of the features, right, that the Poisson random graph, the limit Poisson random graphs have. The large component, right, the small islands, so on and so forth. And it's also true, by the way, I didn't say this, but if you were to look at the giant connected component of these Poisson random graphs for a mean degree, which is just slightly greater than 1, they do look very much like spanning trees. They don't kind of have multiple loops and paths within themselves. And it's only when Z gets bigger that you begin to get a richer kind of connectivity structure, for whatever that's worth. Okay. Here's another graph of a school. I guess sociologists like to go to schools. This is done by Jim Moody, and I believe that the school was in Ohio. And the purpose of showing you this graph is to illustrate some other things. There's all kinds of fancy software out there for drawing graphs. And you draw these graphs in particular ways in order to exhibit particular features. And here the authors wanted to show two things. So the way to look at this graph is that these are 6th and 7th graders in what in America is called a middle school. Right? They typically might run from 6th grade through 8th grade, or maybe occasionally 6th grade through 9th grade. 7th graders are up here, 6th graders are down here. Okay? The colors of the dots indicate ethnicity. Okay? Yellows are whites, greens are blacks, pinks are Hispanic, I believe, or maybe they're Hispanic and other, because there must be some other there, right? Okay, so in any event, and what we are supposed to observe here in this network, and then what they did was they drew the graph in such a way to highlight this feature here, that there seems to be a lot of clustering. And we see the clustering in two ways. There's some, a reasonable set of connections between, there's a small group of people that actually interact across age, 6th graders and 7th graders. But a lot of people who don't, right? We've got this, that's why we have this donut in the middle, this hole in the middle. Right? It looks like a torus, like a donut. You'll notice also that friends are close together. Okay? These are drawn so that friends are close together. That's how these algorithms work. And you'll notice that there is a lot of clustering by ethnicity. So that whites are mostly friends with whites, greens are mostly friends with greens, blacks are mostly friends with blacks. The density of others is sufficiently small that they don't really cluster that much. Okay? Now this property of clustering is very important in social networks. See if I want to make sure I want to talk about this now before we. It has a name. There we are. It's called homophily. Okay. And the idea is that like attracts like. that people tend to be friends with people or tend to be connected with people like themselves, okay? This has implications for all kinds of things, right? Let's, for a moment, think about, for example, using a network for job search, right? Would you want to go and talk to your best friends? So here you guys are all in PhD programs, right? Or beyond, right? How many of you are in a PhD program at the moment? Right? Okay, and you're going to be looking for jobs, right? In a couple of years. Are you going to call the people who you know, graduated a year ahead of you, who you were good friends with? You're going to say any job at your place? How many of you think that's a good strategy? Okay, well, you can do that, right? But the thing is that they're like you, right? And they're, you know, the stuff that you know is likely to be the stuff that they know too, right? Because they're like you, they're your friends, right? What you really want to do is you want to find the person who you met at some conference, right? The person from a very different school who you met here. You want to call them up and you want to say, what do you know about jobs? Who's looking for what I do? Because they, being at a different school, having different information sources, even though you haven't contacted them very much, they're likely to know things that you know, is not known in your circle. So when we call our friends, it's easy to make those phone calls, right? Okay, because it's, you know, they're your friends. But on the other hand, it's kind of an echo chamber. Why? Because of homophily, right? Your friends tend to be like you, they tend to know what you know, right? On the other hand, you call a casual acquaintance, okay, you're more likely to hear something different, right? So now think about the question, what is an efficient way to search? Okay, it's cheaper in some sense to call the people you know, but it is more productive to call the people that you don't know very well, right? And so, interesting optimization problem, right? And I'll buy a beer for anybody who solves it before the end of the lecture. Right? It's a really hard problem to solve. There is one paper on it that I know of by a guy named Scott Borman. It appeared in what was then called the Bell Journal of Economics and is now called the Rand Journal of Economics. It's not a satisfying paper, but it's kind of the state of the art, so it's actually worth taking a look at. Transitivity, we've already talked about transitivity. This is now thinking about what do we see in social networks. I don't have anything more to add to what we've already talked about. Centrality, okay, let's talk about centrality. Who's important in a social network? Let's go back to the problem of figuring out we are the agricultural extension people in Ghana, and we want to get people to grow pineapple, we want to help them grow pineapple, or maybe we're agricultural extension in India, and we have some improved variety of rice that, you know, has all these good vitamins and things like that. Have any of you heard of something called beta-carotene rice? Ring a bell? Right? So, you know, there's been all this adoption, and now there's this disadoption. It's very interesting, right? And you want to get people to adopt this for all kinds of reasons. Who do you contact, right? You want to find the important people. Well, how do we measure importance in a network? That's the question, right? The answer is many ways, okay? So let's talk about some of these ways. Degree centrality. Who is the person who talks to the most people? Okay, that's one question. And so your degrees, the people who have the highest degrees in a network might be there's an argument to be made that they are the most central people because they directly reach the most people, right? Now that's why this might be a good measure. Talking, you know, it makes sense to find the people who have the most contacts. On the other hand, it's not maybe so wonderful if you think about it a little more, because it might be that the people that they have all these contacts with are all the other people who have these contacts, right? So it's just this group of people that are talking to themselves very densely, right? And you're not necessarily getting a lot of spread into the network, okay? So maybe that's not so wonderful. Between this centrality, how likely is this vertex, let's take a vertex and ask, is it central? According to betweenness centrality, okay? Is it, and what do I mean by that? Is it on the shortest path between any two people, between many pairs of people? So one way, why might we be interested in this? Let's suppose, think about passing rumors on a network. You know, I tell you a story with some probability, you tell him a story with some probability, you tell her, right? Always with some probability. How far do you think that story goes? At some point, the chain stops, right? 1 over p is the expected length of the chain, where p is the transmission probability. Okay? So, information is more likely to reach more people along short paths, along geodesics, than it is to go through very, very long paths. Okay? Consequently, if we can find someone who sits on a lot of geodesics, there is going to be the least decay in the information that they have. Okay? And so that's an argument for this notion of centrality. Again, on the other hand, it might be that this graph just has lots of loops, right? And so again, it might be that everybody is talking only to people who are on other geodesics, right? Closeness centrality, I don't even know how this is operationalized. This is one version. And then eigenvector centrality. Eigenvector centrality is very interesting. How many people have heard of something called eigenvector centrality? You have. How many people actually use eigenvector centrality in their daily life? How many people search on Google in their daily life? Right? If your hands weren't up both times, you are liars. Okay? Because how do the Google algorithms work? The Google algorithms are based on, by now of course they're dramatically evolved, but they're based on this idea of eigenvector centrality. What do I mean by eigenvector centrality? Exactly that you are influential if you influence other influential people. Okay? And this idea is due to a name that Stephen mentioned earlier, Phil Bonisic, who is a sociologist at UCLA. And I have been at several conferences with him, and I've never heard him actually speak at a dinner or anything like that. So I don't think his social centrality is not very high, which is interesting for a sociologist. All right. Let's talk about how one might actually implement these different concepts and look for some relationships between them. This satisfies my urge to be a theorist, because we can do a little theory here. So I'm going to suppose that we have a weighted adjacency matrix. I want to think again about this story where I am going to be influenced by the average of what people I am connected to do or say, okay? So it's going to be those AIJs, right, is the amount that J influences I. And again, the weights are going to be different, okay? Some people are going to be highly weighted, some are going to be not so highly weighted. Maybe they're not even going to be averages. Maybe this is just a generalized strategic, let's actually do it this way. So this way we can also talk about incidence matrices. Let's just suppose that we have a weighted adjacency matrix, which is a non-negative matrix, okay? And we're going to suppose, one such story is just to say that we're looking at the unweighted incidence matrix. Another one is to say that we're looking at an averaging matrix, so on and so forth. How do we define, actually, I guess the way that I started this is by saying, I've defined all this stuff for weighted matrices, so we can do this. Here is a definition of degree centrality for a weighted matrix. If this were an unweighted matrix, this would just be the in degree of individual J. How many lines, how many links are coming into J? Okay. When it's weights, we multiply them by their weights, and so here is an expression for that. Okay. So here's another notion, which is due to a guy named Katz, 3/4 of a century ago. He says, so let's think about powers of this A matrix. And let's suppose just for a moment that A is just a regular social matrix. It's just zeros and ones. Okay. So Aij is 1 if there is a link between I and J, and 0 otherwise. So how many links of path 1 can there be between I and j? I'm sorry, that's a horrible thing to say. How many links of length 1, how many paths of length 1 can there be between I and j? There can be at most one, right? Just that edge, the ij edge. Okay? Now let's look at the matrix A squared. Okay? What is the formula for the matrix product? The ijth element of the matrix product A squared. Just remember your matrix multiplication formula. You may not be silent at this point. If you can't multiply matrices, I'm going home. So quick, what is the matrix multiplication formula?
I throw and J following.
Right, the way I think of it is, if I can do it, this is really bad, I do that, right? Right. Summation AIK, AKJ, right? Okay, so so we have the sum of a bunch of monomials, right? And when is an AIK, AKJ pair? When is that product 1? It's 1 when both AIK is 1 and when AKJ is 1. In other words, it's 1 only when there is a path of length 2 between I and j going through k. Okay? So when I sum over all k's, what am I doing? I am counting the number of length 2 paths between I and j. Okay? So a squared is the number of length 2 paths. A squared ij is the number of length 2 paths between I and j. A cubed ij is the number of length 3 paths, and so on and so forth. So what we're doing is we're just counting the number of paths in this formula on the left. We're counting the number of paths between from I to j. Okay, this is, remember, j now influencing I. We're counting the number of paths that go between them. But what we're doing is we're discounting longer paths relative to shorter paths. Alpha is going to be a number less than 1. Okay, and so this is, you know discounting, right? You guys have all done macro, stayed awake, I hope, and so that's what we have. Now, I actually think it's useful for a lot of analysis to just add 1 to everything. Okay, in other words, we'll say that you influence yourself, right? And therefore, and if you do that, you get this very nice expression, which I call CA sub alpha, which is, and what is that? We're just adding here k equals 0 to the sum, right? So in fact, what is this? This is just the von Neumann expansion of I minus alpha A inverse, right? It's the von Neumann series representation of I minus alpha A inverse, right? The problem with this as a measure is that the actual magnitudes change, can go off to infinity as alpha gets very large, right? So a clever thing to do, and by the way, that once alpha gets bigger, there's something sitting in the background here called the Perron-Frobenius theorem. How many of you remember the Perron-Frobenius theorem? You've all heard it, I'm sure. If you have a non-negative matrix, right, then it has it has an eigenvalue which is a maximum modulus among all of the eigenvalues, which is real and positive. Okay, it's ringing a bell. If the matrix is irreducible, well, I don't want to go into the whole theorem, but the point is that the largest there is a largest eigenvalue, right, which is positive. And if alpha gets bigger than that, then the von Neumann expansion explodes, right? So this is only well defined for alpha less than this number lambda, which is this maximum modulus real eigenvalue. If you normalize things this way, it just turns out, you can do the math yourself, that this number stays bounded as a function of alpha throughout this range. And so this allows you to compare these numbers realistically with different values of alpha. Because the question is, in any application, what should alpha be? All right. Moving on. Eigenvector centrality. So what's the idea? Remember, the centrality of J is proportional to the sum of the centralities of the nodes that she influences. Okay? Proportional to the sum. So we're going to have a vector C, which is our vector of centralities. okay? We're going to weight those, of course, by the degree to which you influence. So if we look at Aij, right, this measures the weight of influence that J has on I. If we multiply that by Ci, right, that is person I's influence times the weight with which person J influences her, okay? Then what we do is we sum that over all I. That's the total amount of influence that person I influence, that's the, kind of in some sense, the total influence that I has, and that J has rather, and then what we're saying that the actual measure has to be proportional to this. There's no reason why there should be a solution with mu equals 1. I'm not saying this very well. I'm doing this really badly, so let me start this again. The centrality of J is proportional to the weighted sum of the centralities of the nodes that she influences. Let's suppose again for the moment that Aij is either 0 or 1. That every Aij is 0 or 1. So then what we have is that this sum here is just the sum of the influences that J has. Right? It's the sum of the influences. It is the sum of the centralities of the person that J influences. Okay? If Aij is either 0 or 1, right, for all elements, this is just the sum of the centralities of the nodes that she influences, and what we're saying that her influence has to be proportional to that. And it's the same proportionality constant for everybody. That gives us the following matrix equation, and you can see is that what we're really saying is that C is an eigenvector of A corresponding to this maximum, corresponding to this positive eigenvalue. Now, as I said, that this connects to an important theorem in linear algebra, and the important theorem of linear algebra says the following: if this network is strongly connected, if there's a path from anybody to anybody else, then this real scalar mu is unique. There's only going to be one positive real eigenvalue, okay? And the corresponding eigenvector also will be strictly positive, okay? And so this is a well-defined object. And again, it just instantiates the idea that says that your influence is proportional to this. Your centrality is proportional to the sum of the centralities of the people that you influence. That's all it says. And its mathematical representation is find a eigenvector corresponding to the positive eigenvalue. I guess the one thing I forgot to say is that if this is irreducible, that corresponding eigenspace is one-dimensional, so there's only one. I mean, up to a scalar, there's only one vector there. And as I said, Google uses this because what did they do? What did they do originally? Anytime you sent in a query, they would construct a graph, right, of a piece of the internet that responded to your queries, okay, to your query, and they would then look at this graph. They would look at the adjacency matrix, and they would say that there is a link from website I to website J, okay, if website J is linked by website I, okay. And then what they would do is they would take that, they would construct a centrality vector, and then what you see on the first page of your Google, of the Google search page, are the first 10 most central. Right? I mean, there's thousands of websites out there, right? There might be. How do you know which ones to put in what order, right? The art is knowing where to find something, right? So what they do is they respond by giving you a ranked list of the most central, according to your response and according to your query. And if you go to the second page, you're seeing less central things and all the way down. My experience on Google is that what I always want is on page 5, right? But that just means that I've constructed my queries badly. So this is what Google originally did, and this idea is actually due originally to a computer scientist named John Kleinberg, who does not own a piece of Google. except he might have bought stock when they went public, but that would be it. All right, I've derived a whole bunch of stuff here that we're not going to talk about, but basically what I want to say is that if we look at this modified cat centrality that I introduced, we can look at it for different values of alpha, okay? And the idea, the main thing to understand here is that as alpha gets large, as alpha gets up to its theoretical limit, this modified centrality vector, cat centrality vector, converges to eigenvector centrality. And on the other hand, as alpha goes to 0, it converges to 1 plus degree centrality. Okay? So you can see that we're kind of moving between these extremes, right, by changing this parameter in the cat centrality vector. Now, why might we care about this? I guess I really shouldn't put this slide there, but why might we care about this? Or before I talk about why we might care about this, let me say one more thing. There are really two sources of centrality. One of them that we've already been talking about is who is it that you're connected to? If you're connected to important people, if you influence important people, you're important. Great, okay? Another thing that is influential is what you bring to the table. So I might be, I might play a role, people might be averaging what I do with what other people do, but if what I'm doing is really, really, really extreme, compared to what everybody else is going to do, everybody else is doing, that moves the average, right? So that's the part that I call what do I bring to the table. If I bring something that's really different, really extreme, that can be influential. So Phil Bonasich had the idea with one of his graduate students of saying, let's combine these things together, and he said that we're going to define a notion of degree centrality which depends upon this a notion of centrality that depends upon this parameter alpha, and what you bring to the table, this vector d, and it's going to be basically a weighted kind of eigenvector type centrality plus this extra thing that you bring to the table, okay? And it turns out that when you compute what Phil introduced here, it gives us d times I minus alpha A inverse. And how do we interpret that? Again, it's by looking at the expansion, again, it's how far does your influence spread along all these different paths of different lengths, assuming that we discount them as we go. Okay? So, this is a modification of the idea that says that it matters who you're connected to. It says it matters who you're connected to, but also what you're giving people when you connect to them. Okay, so let's see why this might be important. So let's go back to this game that we introduced at the very beginning. Okay, same game, and you can compute the equilibrium for this game, and I've computed it here. Okay, again, just by looking at the first order conditions, writing them out in matrix form, and all of that. And you get this is the vector, so we have n people playing this game, and this is the vector of equilibrium strategies. Okay, and this comes from the first order conditions. Interesting question to ask is, what is the average play in the population? Okay, and so here I've computed the average play in the population. E is the vector of all ones, so 1 over n E dot x is just the sum of all the x's, xi's divided by n. It's the average in the population. The average play in the population, just do the calculation, and it turns out to be a number which is proportional to, well, what do I want to say again? I want to say, what is individual i's influence on the average choice? Here's the average, and the average depends upon this coefficient n on h. So the question I want to ask is, what is the effect on the average play in the population of changing hi? What person I would do by him or herself? Okay? And the answer is that marginal effect is 1 over n times this expression, which is proportional to Kat's centrality for this number b, which is essentially telling us something about the importance of the public term relative to the private term. The more important the public term is, the larger that this phi is, and the more nearer we are converging to eigenvector centrality. Okay? The smaller phi is, the more we are converging all the way down to the limit at the end being just one, just yourself. Okay? So here we can see how these concepts from sociology actually play a role in helping us understand, right, the solution, characteristics of the solution to a non-cooperative game. Right, the same one that we started with. All right, clear? All right. How much longer do I have? 15 minutes? Right. But didn't you say I could go on as long as I wanted?
Feel free.
Good. Anyone busy until 6? All right. All these quotations come from papers of Stephen Durlock. No, Stephen didn't write this. He just quoted some guy who did. Who is this Aristotle?
You caught my plagiarism.
Yes, I did. All right, so homophily, we mentioned the idea of homophily. Homophily is this idea that that friends like friends, right? There are multiple sources of homophily. Status homophily, that we feel more comfortable when we interact with others who share similar backgrounds. So I have a bunch of attributes that describe who I am. I tend to be connected to people who share my attributes. I can tend to be connected to people who share my beliefs, which are different from my attributes, my characteristics. Those are two that the sociology literature writes about. There's a third that only an economist would think about, which I call opportunity homophily. It says that there's constraints in the world, right? And I only tend to be connected to people who I actually have a chance of meeting, and those people tend to be a lot like me. Right? The people I meet at work are a lot like me. I tend to know a lot of economists. You should see my Facebook friend list. Really boring. Okay. I think I won't talk about that. I just want to go and talk about labor markets, and then we'll finish with this. Let's think about search and how do people find jobs. This is a table from a paper written by a former colleague of Stephen's, Jim Montgomery. He's a very interesting guy because he has a PhD in economics, but he chose to become a sociologist, thereby lowering his salary. And he's in the sociology department, right, at Wisconsin. And he wrote some very interesting papers in the early 1990s. This one is from the AER, as you can tell by if you recognize that style up at the top. And here, this is a summary of different studies that have been done over the course of 30 years. And by the way, if you were to extend this list up until today, this paper comes from the early 1990s. If you were to extend this list up till today, you would find the same fact. And that is that when we look at how people find jobs, right, what percentage of people in the surveys found jobs according to these different methods? Friends and relatives, just applying at the door, going through an employment agency, reading the newspaper, something weird, okay? And you can see that in all these studies, it is friends and relatives that dominate, okay? So what we learn from this is that social networks of some kind are very important in finding jobs. Right, that's the takeaway here. Now, some of these surveys, they didn't all ask the same thing. None of the ones that are reported here actually disaggregated friends and relatives so that we could kind of find out more about the nature of the social relationships. But in fact, this was done in the PhD thesis and off and on throughout his career by the distinguished sociologist Mark Granovetter, who is on the faculty at Stanford. And he introduced the idea of making a distinction between what he called strong and weak ties. Okay? So, strong ties are people that we're very strongly connected to. Think about what that might mean. Weak ties are people that we have a much more relaxed, much more occasional connection. We can operate this, and here he's kind of talking about how you might operationalize this concept. Okay? But the way that he actually chose to operationalize it in his own empirical work was to say, how often do I talk with you during a given period of time? If I've only talked with you once or twice during the past year, you're a weak tie. If I've talked with you a lot during the last year, you're a strong tie, and we will operationalize this by choosing some threshold. And if you're above the threshold in contacts per in the window, that's a strong tie, otherwise it's a weak tie. And he had this idea that weak ties are important because they reach out, because they take us to different places in the social network where people might know different things. Exactly what I was saying earlier about job search, right? That weak ties might take us to new people. So here is the idea that Granovetter had. And let me again look at my notes to make sure that I say this in an efficient way. Because you can see that as I've worn down here, I tend to become less efficient in my talk. Okay. Okay, so Mark Granovetter had the following idea. He said, I just want to make a hypothesis about graph construction to show how weak ties can have reach in a graph. And his idea was the following. He said that if I have two individuals, let's suppose that I have three individuals, A, B, and C. He says that if A is strongly connected to B and B is strongly connected to C, then there should be some kind of link between A and C. In other words, we would expect to see transitive closure when two of the links are strong. Okay? He says, but weak ties, people that you occasionally see, not necessarily true, right? So if I bump into some person, just because we happen to, ride the same bus in the morning, and so we might have a chat while waiting for the bus or something. And then there's somebody else who they see, at the water cooler at work or something like that, and I work, in a completely different building, so on and so forth. I'm not likely to know their water cooler friend, right? But on the other hand, if he and I are in a carpool together and we drive to work all the time, well, then maybe we get together at occasional parties as well. I might have an event and invite him. I'm going to know some of his friends. He's going to know some of mine. That triadic closure is much more likely. Okay? So he wants to explore the idea. So what does a graph look like when we have this triadic closure property, namely that the triangles consisting of two strong ties are in fact closed in some way. So here we have two cliques that are disjoint, and I've distinguished two people, A and B. And I've drawn now a link between A and B, and I'm going to call this link a bridge between A and B, because this is the only path between A and B, okay? And so this A-B link is important because it can carry information from the back and forth between the two connected components here, between the two cliques. They are cliques. Yes, they are. Okay. So now let's add another link, okay? I really can't say that A and B is now a bridge anymore, okay? But I'm going to say that it still has a special property. I'm going to call it a local bridge, okay? And I'm calling it a local bridge because the endpoints have no common friends, okay? So if I look at A and B, A's friends are these three, B's friends are these three, and there's no commonality in them, okay? So it is still the case that this tie is bridging between this group and this group. There happen to be two such bridges. Just think about a city with 2 or 3 bridges going across a river that splits it, okay? Each bridge is still importing, is providing a local function, an important local function, and that's exactly what's going on here, all right? Okay. So now let's, in fact, label the ties. And you can, I've just chosen one labeling here, but there are many ways that you could label them. Okay, but I am using the Granovetter rule, which says that a length 2 path consisting only of strong ties is in fact a closed triad. So, for example, I've got a link from here to here and a link from here to here. They're both strong, and that means there's got to be this tie here. I've made it a weak one. I could have made it a strong one. Okay. Here we have strong, 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 okay? Again, so I'm using this property of triadic closure. Notice that these local bridges are still local bridges. Suppose that this were a strong tie, okay? If this were a strong tie, then this is strong, this is strong, and therefore this AD link would have to be there, and this red line would no longer be a local bridge. Why? Because there are friends in common across. Okay. Similarly here, right? Strong tie. No, not at that end. Yeah, strong tie here. Strong tie. If this were strong and this is strong, okay, then in fact this line here would have to be there as well, and again there would be common friendships across the bridge. Okay, and so this line here would no longer be a local bridge. The point is that when we do this labeling according to the Granovetter rule, right, any local bridge has to be a weak tie. Okay, if we think that triadic closure of some kind is a property of strong ties or strong tie length to paths, okay, then we can see that the links for jumping across here from here to here all have to be weak. And that's the importance of weak ties, okay? Granovetter did some empirical work trying to figure out what went on in labor market search, and let me see if I can find what he had to say. So Granovetter looked at a bunch of people who were changing jobs in Newton, Massachusetts, and he asked those who found a new job in the year that he was looking at them, found a new job through a contact, how often they saw the contact. He wanted to know explicitly his way of operationalizing ties was by length of or frequency of contact, and he wanted to know whether people found jobs through strong or weak ties. And the answer is that very often the tie, I have numbers here. He said that I asked people whether they found the job through people who they saw often, occasionally, or rarely. And it turned out that more than half of the jobs were found among people who found jobs through contacts, found those jobs from people who they saw only occasionally. Not rarely, they didn't even tend to ask people they saw only rarely, and not often, because the often stuff just wasn't that productive. This study has actually been replicated in a number of places, in a number of countries. It's been replicated in China. It's been replicated here in Russia by a guy named Valery Yakubovich, and in 2005. It's been replicated in several countries in Europe and in South America. That these are the kinds of ties that matter. I want to conclude by talking about a model that shows us how it is that ties might actually have and social structure might have an impact on market outcomes like wages and employment and so on and so forth. Okay, so I've been talking about a lot of sociological contact, sociological material through looking at it through the eyes of an economist. But what I want to do is close by showing you how these concepts from sociology in fact can inform economic analysis and have something to say about economic variables in models of the kind that we care about traditionally. Okay, so this is a kind of inverse empiricism, or I'm sorry, an inverse intellectual imperialism. This is why not just that we should be going out and conquering the fields traditionally reserved, or topics traditionally reserved for sociology and psychology, but on the other hand, how they can inform what is in our traditional domain. So this is again, a very simple model from this paper by Jim Montgomery. And here's a description of the model. Workers live for 2 periods, fixed number of workers the same in both periods. This is going to be a very familiar model, I think, to many of you. Half of the workers are high ability, half of the workers are low ability. Workers are observationally indistinguishable. If you hire someone, you can't tell who they are. Every firm, there's free entry of firms. Each firm employs 1 worker. The profit to the firm is the employee productivity minus the wage that he has to pay the worker. Okay? Makes sense? This is all pretty straightforward. What is the equilibrium condition in this market going to be? Let's just imagine this market now. It's just all anonymous trading in labor markets, right? The equilibrium condition is going to be, because of free entry, that firms' expected profits are 0. And if firms' expected profits are 0, right, then what is the wage going to be? The wage is going to have to be expected productivity, right? Which, since our productivity is either 1 or 0, and the frequency is 1/2, the wage is going to have to be 1/2. That's equilibrium, right? That is an undergraduate test question. Okay, so now let's put in some social structure. Remember that we have 2 periods here, and we have workers at time 1 and workers at time 2. Every worker at time 2 knows at most, every worker at time 1 knows at most 1 time 2 worker. Maybe you don't, you're an old guy, maybe you don't know anybody, maybe you know 1 person, okay? Every time 1 worker has at most 1 social tie, the probability of having a social tie is probability tau, which we'll refer to as the network density. Ties, of course, are IID, all right? So the network density, larger tau, the more ties we have. Conditional on having a tie, it may be to the same type of worker that we are, it may be to a different type of worker. Alpha measures the probability that it's to the same type that we are. We're going to require alpha to be greater than 1/2, so it's more likely that we're tied to people who are like us than people who are not like us, okay? This is homophily at work, all right? Everybody with me? Okay. All right. Now, the tricky thing in this model, and it is a little bit tricky, is that every time 1 worker has only 1 time 2 friend, okay? But it could be that, that Stephen and I, old workers, right, have 1 young worker friend in common, okay? So we might be tied to the same person, right? So the time 2 person, right, has 2 time 1 ties, but every time 1 person has only 1. Clear? Okay. All right, so here's how the market works. In the first period, workers are hired anonymously. There's a market clearing wage, then there's production. And then afterwards, now we go into the second period. Beginning of the second period, each firm can or cannot choose to turn to his worker and say, if you refer me a worker, I will hire that worker, and here's the wage rate I'm going to pay that worker. Okay? Social ties, Jim says they happen here, but in fact they could happen anywhere. They could happen back here. Team 1 workers relayed their referral offer if there is one. Time 2 workers decide either to accept the offer or enter an anonymous labor market. Then the anonymous labor market clears and we all go home, which we're about to do anyways. Okay? You hope, right? All right, so what's the equilibrium going to look like? Much of it is obvious. Only firms with high productive workers are going to allow referral offers. Why would you want to get someone who's less good than a random draw? Okay? Since productive time 1 workers are more likely to be linked to productive time 2 workers, the fraction of time 2 workers who have to go, the type of time 2 workers that have to go into the anonymous market are more, they're going to be more likely to be unproductive workers. What are they going to be in equilibrium? They're either going to be unproductive workers who did not get a referral offer, or productive workers who unfortunately had no friends. Okay? And since that's a subset of the whole, that means that the anonymous market is more likely to be filled with unproductive workers, and so that wage rate is going to fall. This is something I don't want to talk about, but because of the fact that a given time 2 worker can have 2 time 1 referrals, okay, there is monopoly power of some kind. There's a little bit of imperfect competition in this market, and that monopoly power, in fact, leads to having a distribution of referral wages. Okay, it starts at WM2 and it goes up to some number R, WR, whatever that is. Expected profits in the second period are positive. Okay, not 0, but positive. Okay, and what about the market wage? This is very interesting. The anonymous market wage in the first period is now greater than 1/2. Why is that? Okay, because what is my value? My value is, if I'm an unproductive worker, my value is 0. If I'm a productive worker, my value is 1, plus the value of the referral that you get from me. Assuming probability, some probability I have a referral, right, and you get to make that, right? So that's greater now than 1, and therefore the expected value, right, of hiring a worker anonymously has to be greater than 1/2 because of this extra little piece. Okay. Comparative statics, what happens as we increase the network density or we increase the degree of homophily? Either creating more links so that more people have more workers have links, making the network more dense, or making the referrals more informative about type. Tau for the first one, alpha for the second one. Well, in all cases, what you're doing is you're making the referral market a thicker and more informative market, so the anonymous market wages are going to fall. Okay? It's going to be better to get a referral. This is not obvious. This is the one thing in the paper that's not obvious. It would have been obvious if you were reading economic theory in the early 1980s when people studied this kind of thing all the time. But it's fallen out of the graduate curriculum. But you can read Jim's paper and see where to go. The top wage is going to go up. Profits are going to go up the more informative and thicker the referral market is. And of course, because of that, the better it's going to be to have a worker who can give you a referral, and therefore the anonymous market wage in the first period is going up. Okay? All right, other stuff that we don't need to talk about. And so I think one of the points is here to keep in mind, and to bring us back to the original theme of this meeting, is that what is the effect of social structure? Well, it actually certainly increases the informativeness of the market, right? But one of the things that social structure here is doing, right, is basically magnifying inequality, right? So we start in a market where the wage rate is simply 1/2 in both periods, and that's it. Everybody's earning the same no matter who they are. As we make the social structure richer by increasing alpha or tau, right, what's happening now is that due to the richness of the social structure, the market wage for uninformed second period, the market wage for anonymous second period workers, those who go to the anonymous market, which includes all those who have unproductive friends, whether or not they're productive, right? Unproductive friends, their wage is falling. The market value, the market wage rate to workers who have productive friends is going up, okay? And profits are going up, right? So in some economic sense, it seems that the equilibrium might be more efficient because we're getting better sorting of workers, but it's also true that coming along with this is an increase in inequality, right? An increase in wage inequality. Now, the take-home thing for you to think about is this a good thing or a bad thing? Is this justified inequality or unjustified inequality? And what could I even mean by justified inequality? Right? When could it be the case that a large Gini coefficient is a good thing to have? And Stephen will answer all of these questions tomorrow. Thank you very much.